All right, so I've got my recording started.
Okay, hello everybody. My name is Anna Krupivnitskaya. I am working at University of Kansas and currently I am based at CERN. I'm very happy to participate in this workshop and I believe that machine learning, this is not the future, but it's a current situation in high energy physics. I also think that most of the analysis currently should include machine learning techniques in their studies to be competitive on the physics market. So let's review one of such analysis today. So I start sharing screen. So today I would like to present you machine learning technique for signal background separation of nuclear interaction vertices in the CMS detector. I would like to pay attention that this is not a tutorial, but code with toy data is available at Bander, and you are welcome to connect to Bander after this session and run code yourself and enjoy it. Oops. In HEP, very often problem of signal background separation appears. For example, this could be resonance peak from decay particle, physics object reconstruction or identification, nuclear interactions with materials. This is the topic of this analysis. Photon conversion with materials, and all these signals appeared on the top of combinatorial background. Very often there is no clean sample of signal to train a neural network, but regions with enhanced contribution of signal could be known, for example, by mass cut or by some geometrical cut or any other phase space cut. Machine learning technique of a neural network with floating classification could be helpful in this case. So input classification is done on mixed sample with different fractions of background to signal, and output classification is optimized for real signal and combinatorial background separation. This analysis is performed with Jupyter Notebook at Swarm platform, and code is available on the GitHub and on the Bander. As I told you before, there is no public CMS data sample for this notebook, but toy sample was generated with NumPy inside of this Jupyter Notebook to show the notebook functionality. So what is a CMS detector? Because maybe some of you are not familiar. This is detectors are designed to study different particle properties created during proton-proton collision. Here you could see a schematic view of the CMS detector. In center of CMS detector, you could find a tracker system, which is designed to detect charged particles, measure their momentum, and also measure vertex of the proton-proton collision or any other secondary vertex reconstruction. After that, it is surrounded by electromagnetic calorimeter, which is detect electrons and photons, hadron calorimeter, which detect hadrons, always inside of the superconductive solenoid, and after it we have a muon chambers. In this analysis, the material of the pixel detector, and this is a small part of the tracker system, is studied with the nuclear interaction. So let's look how our pixel detector is look like. So it's a schematic view, and pixel detector consists from the two parts, from the barrel part, we call it BPX, and the rest is a forward part, which we call a forward pixel. So our analysis is limited with the barrel part of the pixel detector, which is consists from 4 layers, layer 1, 2, 3, and 4. This detector is situated just near beam pipe, and beam pipe, this is the vacuum tube where proton-proton collision occur inside of the CMS detector. So what is now nuclear interactions? It's an interaction of hadrons with detector material which creates secondary vertices inside of our detector. For physics analysis, nuclear interaction play the role of the background or noise in the data. But due to its interaction with material of the detector, the positions of these secondary vertices map the material with a sub-millimeter precision. And accurate knowledge of the positions of active and inactive elements is important for simulation detector, for planning detector grade, and reconstructed charged particle tracks also. This analysis is based on the proton-proton collision, and we used part of 2018 data. Nuclear interaction reconstruction technique is described in these two papers. If you are interested, you could look inside of them. Briefly, nuclear interaction is just simple displaced vertex with some requirements. We require at least 3 tracks incoming or outgoing from the vertex. And here you could see schematic view, for example, of nuclear interaction with income track, which is marked as red, without income track, and with the merged track. Also, we apply some invariant mass cut of the ongoing system above 1 GeV to suppress light mesons, baryons decays, and also photon conversion. As I told you, in this analysis, we analyzed only barrel region. That is why we select 1.5 million nuclear interaction candidates. So, how we map our detector with the nuclear interactions. Here, in this plot, I present the XY view of the nuclear interaction inside of the pixel detector. So you could see nuclear interaction just occur inside of the material. So here you could see the most inner circle, it is a beam pipe. Afterward, layer 1, layer 2, layer 3, layer 4, outer shield. Also, there is the inner shield, but it's between beam pipe and layer 1, and it's not visible here. After, pixel detector support tube here, and also a pixel detector support rails. And I would like to pay attention that rails, they has no cylindrical structure. It's horizontal plates in the top and bottom of the detector. We need to know it in next slides. So as you could see, we could really well reconstruct detector with nuclear interaction, but we could see that in the beam pipe region, layer 1, layer 2, and layer 3, we have a huge combinatorial background, which we would like to suppress. So for each nuclear interaction candidate, we could monitor variables, which are very similar for real nuclear interaction, our signal, and combinatorial background, our background. Machine learning technique could be helpful for signal background separation in this case, and a neural network with 2 hidden layers with 12 neurons in each hidden layer is selected. For simplicity, only vertices for a nuclear interaction candidate with exactly 3 tracks are used. This is majority of the vertices. So 23 variables are injected to the input layer of the neural network. This is number of primary vertices, number of nuclear interaction candidate per one event. And for each track in the vertex, we have 3 tracks. We have transverse momentum, eta phi coordinate. Also, we have a fit quality. It's a high square, normalized high square, number of valid hits, and track reconstruction algorithm. The vertex position is used for classification of nuclear interaction candidate. And I would like to pay attention that it is not injected as an input variable for the neural network. So how we perform a classification? Classification for signal and background regions is done by using the radius of nuclear interaction candidate, which is defined by this formula, where xy is the vertex position of the nuclear interaction, and x0, y0 is the position in the CMS coordinate of the material structure, which are installed with millimeter precision, and they are taken from this publication. And they are listed in this table for the beam pipe, for the BPX, and for the rails and support tube. So classification is done in 7 regions. We define them as S0, S6 on the next slides. And for 5 background regions, we defined it as B7, B11. So now we are ready to move to the classification around beam pipe. So what we do, we plot nuclear interaction density as a function of radius centered at the beam pipe. And you could see very nice peak from the beam pipe. So we classify this region as S0, and also we classify the background as B7, near beam pipe. I would like to pay attention that we don't make any classification on the right side, because there is a contribution from inner shield and layer 1 BPX detector. Background signal ratio for the beam pipe region is estimated at S0, and from side bands, and it is around 0.16. So we have a small contribution of the background for the beam pipe. Now we are ready to move to the pixel detector. So pixel detector is slightly more complicated. You could see that we plot a radius as a function of the centered at the B peaks. And you could see a nice peak from the inner shield, from layer 1, from layer 2, from layer 3, 4, and outer shield. So we make a classification from S1 to S6, and also we make a classification for the background regions from B7 to B11. Also, we calculate a ratio, background signal ratio, and it is appeared that it's varied from 2.6 for the inner shield. So we have 2.6 more background than signal, up to 0.17 to the layer 4. So we will return to this question later that we have so much background in our signal regions, what we will do with it. So now we make a classification for the pixel detector support tube. So it's a similar thing. We plot a radius and we define the signal, also with a small contribution of the background. And for the rails, I told you before that rails, they don't have cylindrical structure, just horizontal plates. So that's why we could make an enhanced region for plates requesting additional cut on the absolute value of X, or suppressed region for rails to make a cut on absolute value of X above 10 centimeter. And we make also classification. Again, for rails, background signal ratio, it's about 0.13, so we have a small contribution of the background in this case. So now we would like to see, okay, how our input variables to neural network looks like. And here it's example how they looks like for the beam pipe region. So blue curve correspond to the signal region for the beam pipe, and orange curves correspond to the background region around the beam pipe. As you could see, small shape difference between signal and background distribution are observed, and only neural network technique could be helpful to separate signal from background in this case. So now we could discuss the data. Data is for us is the nuclear interaction candidates, and they are presented in the NumPy matrix X. Each column represents 23 input variables for neural network, plus 3 variables for vertex position, which we use for classification. Each row represents a new nuclear interaction candidate. Classification for neural network Y-true set include 2 classes calculated by using signal and background region, which we defined on the previous slides. So class 0, it's our signal class, includes beam pipe, layer 2, 3, 4, rails, and tube signal regions. I would like to pay your attention that inner shield and layer 1 signal regions, due to high background contamination, are not classified as a signal class for neural network, so they will be not used during training. But we shouldn't worry too much about this, because input variable distribution in the beam pipe region should be similar to the inner shield and layer 1. And also it will be a great cross-check for neural network signal background separation power in non-trained signal regions. Class 1, background class, it's all classified backgrounds. I would like to tell that some nuclear interaction candidates, including, of course, inner shield and layer 1, regions stay in non-classified state. They are not used during training. So let's talk a little bit about our classification, Y-true. It is done again on the mixed sample, because our signal class 0, include real nuclear interactions and combinatorial background. For some structures, background signal ratio reach almost 1, so it's 50% of the signal, 50% of the background. Background class 1, include mostly combinatorial background in our case. Neural network model is trained on the mixed sample and calculated the probability distribution, which I call p-signal, for the injected vertex to be a signal. The predicted classification Y predicted is estimated by optimizing cut on the p-signal for real nuclear interaction and combinatorial background separation. This will be shown later. This is an example of neural network model with floating classification. So input classification is done on the mixed sample with different fraction of background to signal, and output classification is optimized for real nuclear interaction and combinatorial background separation. So meaning of our classification is changing during training. This technique is very similar to Koala method, which is described in this paper. So when we classify data, we are ready to shuffle data to avoid runtime dependent correlation and divide our data into the train and test set. We divide it in proportion 50 by 50% only because we don't have much data. So we need a lot of data for training. Such way, test and train set, it includes around 0.7 million nuclear interaction candidates.
Anna, could I stop you for an inline question? Which
Yes.
is, what are the definitions of signal and background in this case? It'll help people following.
Okay, we return on this slide. So I could tell the definition of the signal and background classification on the input. This is our S0, this is our mixed definition, yes? Because we have, for example, when we make a classification, we have mixed samples. And sometimes under some structures, these samples include half of the signal and half of the background. So input classification is done really on the mixed sample. We tell, okay, this our signal, and what I mean our signal, this is this guy, it is our signal.
That's what I was wondering.
And here, this is our signal, so it's mixed. But after that, on the output classification, we optimize for real nuclear interaction and real combinatorial background. So you see, this classification is changing. That's why I call it floating classification. But in the beginning, it's have one meaning, and in the output, it's have another meaning.
Yeah, I was just asking definitions of signal because it can vary for an analysis like this.
Definition, real definition of the signal, it's our real nuclear interaction, which is interaction with the material. And the problem is that when we construct nuclear interactions, that it's very often we have a random combination of the tracks which give us shifted displaced vertex. And these random guys were here, they're in the B11 region, they're in the B8. This is all random combinatorial vertices. It's not a real vertices from real interaction with material. It's a random vertices.
Great. Okay, thank you.
Okay. Okay, yeah, so we split our data set for test and train. After that, we normalize each input variable in the X-train set on its mean and standard deviation for better performance. And we perform a principal component analysis on input variables in the train set. So for those who are not familiar with PCA, PCA is defined as an orthogonal linear transformation that transforms the data to a new coordinate system, such way that first PCA variable has greatest variance, second PCA variable has second greatest variance, and so on. When we apply PCA to our analysis, it shows that all 23 variables after PCA transformation have significant variance. Of course, the last variable have the most smallest variance, but it's still pretty significant. That is why all PCA variables were kept for the injection to the neural network. Test set use the same normalization and PCA as a train set. For the model training and validation, only classified events are used, so it's only our class 0 and 1, and it is 0.4 million events in total. For the model prediction, all events classified and not classified are used. So now we are ready to train our model, and here as a loss function, it was chosen categorical cross entropy. So this is the function with which we minimize our model, and we could see how it's evaluated during training. So here you see a loss function as a function of the epoch. Epoch, it's a number of passes of the train set to the neural network. You could pass it once, twice, thrice, and 300 in this case. As you could see, test and train loss distribution are very close and are decreasing during training, which show that model is not over or under-trained. So now on this plot, this is the output of the training. This is the probability distribution after neural network model train. of the nuclear interaction candidate to be a signal. So it's our P signal. And it is used to predict classes of the neural network output yPredict. So how we do this prediction? We classify yPredict as a class 0 if P signal above some P cut, and the rest, this is a class 1, it's our background. For signal background classification, PCAT is optimized with maximizing F1 score, which is defined here, and is calculated on real nuclear interaction and combinatorial background, which require high precision. In physics, we call it purity, and high recall in physics, we call it efficiency at the same time. I would like again to pay your attention that FI score is calculated on real nuclear interaction and combinatorial background estimated from the sideband, but not on the signal and background classes prediction yPredict, because our signal class, it still will include some combinatorial background. So now we are going to the next slide, and here we could see how our optimization with this F1 score looks like. And the optimal cut, it is appeared P signal equal 0.47. So this cut was used for prediction of the model for the to be a signal or background. So now, when we have our predicted values, we define them, how we are ready to look on the results. First of all, we start from the train set. And I would like to tell that this is only for the cross-check. So what we could see here, we could see a radius distribution centered at the BPX center for our train set. Blue curve corresponds to the signal class, and orange curve correspond to the background class. And this is our prediction classes. So as you could see, neural network models suppress background by factor of 4 or 5 for train set and keep around 90% of the signal, our real nuclear interaction in the signal class. And in background class, we mostly have a background. I would like to pay attention that neural network wasn't trained on the inner shield and on the layer 1, and you could see it still have very well performed, and it's as well performed as a beam pipe. So, okay, train set, this is a set on which we train models. So now we would like to look on the real results on the test set, yes? And if you go to the test set, you could see that there is no much difference. Our model is performed as well as on the train set. So its main results, and they're very similar. And this is in principle what we should expect, because I show you that our loss function for train and test set is very, very close to each other. So it means that performance should be very, very similar.
Excuse me, in the interruption, Anna, just letting you know you have a couple more minutes before we should break for questions. And also just a reminder to the audience to submit your questions on the Slido link in the chat.
Okay, I almost finished. So now we are on the slide 22. And on this slide, we could look how our numbers evaluated, how our background to signal ratios, which we discussed before, in our signal regions, which we defined only by geometrical cut, by radius cut, how these ratios are changed. So first column, it's represent our data without any classification. So this is how our background signal region in our geometrically defined regions, signal regions, look like for the beam pipe and all other structures. And also you could see in the second and third line results for the train and test set. So you could see that we managed to suppress this ratio background to signal more than by factor of 2. So this is a really impressive results. And now we also could look how our mapping of the detector in XY plane change. And here it's a zoom region around beam pipe and first pixel layer. Top plot corresponds to the data without any classification. You could see a beam pipe, inner shield, and layer 1. Bottom plot left correspond to classification with a signal class, and bottom left, it's a background class. So it's do really, we have impressive separation, and most, we suppress really a lot of background. Also, we could look how it's look like in more zoomed space, including layer 2. And you could see between layer 1 and layer 2, we also very well clean background. So This is nice. So now we're moving to our conclusions that a machine learning method for reducing combinatorial background in data without Monte Carlo technique, this is very important, is presented. Neural network model with floating classification on mixed sample is constructed, even through the variables used for the training show only a small difference between background and signal. Neural network has impressive separation power. We didn't train our neural network on the inner shield and layer 1, but it still have a very impressive results. And combinatorial background suppression could decrease systematic uncertainty for material position and material density measurements. This technique could be used for any analysis where you could perform classification on mixed samples with different ratio of background to signal. And I would like to thank NSF for the support of this analysis. And please don't forget, if you are like machine learning or would like to study it, please follow the binder and run this code offline for yourself. Thank you for your attention.
Thank you so much, Anna. That was a really nice talk, and great to see those results. So I'm going to stop your sharing so I can bring up the questions on Slido.
Okay, I did it.
Thank you. All right, so this is it's a nice set of questions. It seems like there's a lot of interest in how you selected, maybe the motivation behind some of the model architecture that you ended up with. So maybe to start, maybe you could comment on some of these questions related to how you chose your loss function, the reasoning behind choosing the ratio for dividing up your sets, and then maybe the consequences of over or under training in this context.
Okay, so I will start from the top question, yes, and follow it. So the first question, can you elaborate on what it means to be over or under trained and how the loss function are able to tell us about that? Okay, yeah, so this is a machine learning technique, yes, when you monitor functions, you could to understand if model overtrained or undertrained. So what does it mean when it's overtrained? Overtrained, it means that your test sample could be a trained sample could be maybe very small, or you have too much parameters for your neural network. So neural network could find the features which with this it could describe this data really perfectly. But it's mean nothing. It means that it's find some features which are not really exist just because we don't have enough data. It's like if you have, I don't know, 2 points and you try to fit with the line, with the parabola. Yes, so it's like 3 points you fit with parabola and you will have a perfect description. Yes. But maybe it is not a parabola, maybe idea it's just a linear, it's a line. But of course, parabola will be more favored, but predictions will be less reliable with parabola. So it means if we don't have enough data and we have too many parameters, that our model could be overtrained. It means that we will have a good prediction on the trained model, but very poor prediction on the test model. Under train, it's yeah, it's under train. It's the opposite thing to the overtrain. Okay, I could see. I also you recommend to look some lectures for the machine learning because it's very well explained when model are overtrained or undertrained. So why was a neural network chosen over another framework, say BDT? I believe that it's very important in the physics not only to use existing tool and don't really to understand how they work, but also try to develop something by yourself. And in this case, you could control things better and you understand the process. And in this case, I just decide that why not to try to use a neural network and to have these results. Yeah. And this is pretty simple data, so you don't need some very complicated algorithm to optimize it. Another question.
And maybe you could address that final question about the cut on slide 19.
The cut you extract, was this done using the training set? So the same data as new was trained on. I will look on slide 19. Okay. Yes, it's true. And it's even written on the slide number 19 that cut which I extract, optimized cut, it was done on the train set, on the set which we trained. And if you notice, I wrote that in principle to be more correct, you have to have 3 samples. You have to have a train sample, you have to have validation sample, and with optimization, you have to perform on the validation sample, not on the train sample. And after that, you have a test sample, and results, final results will be on the test sample. But due to limited of the data, I perform this optimization on the train set, and this is what could be done, what it could affect. It could affect that maybe we could even achieve better performance for the test set if we have an extra validation set. But in our case, it means that we only could slightly lost something on the results on the test set. But you see, even with optimization on the train set, we still do really have impressive results on the test set. But yeah, it's true that optimization should be done on the validation set.
Yeah, so maybe just that was my question. So a very small comment then on that, but I feel like I have to say is, I think you should not do that on a train set because you can really bias yourself, and it doesn't say a lot how optimal your cuts is. You should really do this on data that was not seen during the training. And in case you said you don't have enough training data, I would highly suggest you to look at k-folding, and then you have enough data because you can like switch things around.
Yeah. Yeah, but yeah, I know that it's a weak point of this part of the analysis, but even with this optimization, you could see that our test set, because I didn't make any manipulation with the test set about optimization, it still have very similar results to the train set, and it still have a very good power separation.
Great. So I want to recommend that maybe we can move the conversation onto the Slack after this talk. Thank you so much, Anna, for your time.
Thank you.